Oh, here. Here too. Which direction? No. Wait a moment. So it should work now? Yes. Okay. Okay. Please start.
Yeah, go ahead. Okay. So this talk is about simply type beta convertibility. So the problem of checking whether two terms are can be converted in one another by application of beta rules. Okay, for the simply type beta and for the safe fragment, something a bit obscure, I'll explain what it is. And gaming all this is still complete. So I'll define all those terms very soon. But so first, for some context, okay, recall what is a lambda calculus. I guess everybody knows this, right? Okay, so grammar of lambda terms is either you have a variable or an application or an abstraction. Okay, and then there was a so you can just study these as static objects, like as trees with binders, etc. I forgot to mention alpha equivalence, but whatever. So that's already an interesting combinatorial object, but there is also a dynamics given by this beta rule here, which allows you to rewrite lambda x dot t applied to u into t where x has been substituted by u. And so this, for instance, has been investigated by Alexandros in his talk this morning. Okay, but he worked in a linear case where everything is very nice. So this always terminates into a so-called normal form, so the terms that you can't reduce anymore. Whereas in the like non-linear lambda calculus, you can have phenomena like this. So if you take lambda x dot xx applied to lambda x dot x, what do you get when you reduce? You know, get xx where these two occurrences of x are going to be replaced by this argument here. But then, okay, you see that you get the same term as you started with, so you have an infinite loop, right? And you can also have things like an infinite reduction sequence where the size of the terms is strictly increasing, things like that. This is very well known. So non-termination is possible, and that's right. Okay, so this is Turing complete. You know, it's one of the original definitions of computability, which was very equivalent to Turing machines. So obviously, okay, because of the halving problem, you are not even going to be able to decide whenever something terminates. And okay, Turing completeness also means that anything interesting that you would want to decide, which is like extensional, is not going to be possible. So typically convertibility of two terms. Okay, so checking whether two terms are related by the reflexive transitive closure of this thing, which I write by equals beta. That is an undecidable problem. So this is for the general untyped intercalculus, and in this talk we are gonna look at this problem here, the convertibility problem in a restricted setting. So the setting of simply typed intercalculus, and I'll start by recalling and clarifying a bit what the state of the art is about convertibility into simply typed intercalculus. And then, okay, I'll present an extension of the result to safe lambda terms. And safe lambda terms are a strict subclass of simply typed lambda terms, and we'll see that the convertibility problem is actually as difficult on safe lambda terms as on general simply typed lambda terms. Okay, so what are simply typed lambda terms? So the idea of typing is just you annotate your lambda terms with some information that tells you how they're supposed to behave. So typically, okay, so when you say that the term t has type a to b, you can interpret that as like t is a function from a to b. So more formally, if you have a term of type a to b and you apply it to a term of type a, you get a term of type b as expected with a function. Okay, and so what is called a symbol type, okay, is just the grammar of types which are just generated from a base type. Let's say let's call it O here by just this constructor, this arrow. So you don't have any features like polymorphism kind of sophisticated things. You just have like a base type and functions. Right? And okay, you have some rules to which allow you to derive the fact that, like, say, f of x is of type O whenever you give the type O to F, and type O to X, because so here you see that the type of the argument X matches with the left of the row, so the type of Fx is what you get at the right of the row, etc. So you can also have rules for lambdas, which I'm not going to write down formally, because it will require introducing a context for the type derivations and make things a bit heavyweight in terms of notation. But anyway, you see that the intuition is that you can say that, okay, since here you have the free variables f of type O to O and x of type O, you just put them on the left of the arrows here. It says that, okay, so the function that takes f and x and returns this f of x. Okay, so its type is going to be, okay, I take this O to O corresponding to f, take this O corresponding to x, and then I return the type of my composite expression here. Okay. So this is typically a way to encode the number 2 in the lambda calculus using something called Church encodings, which will maybe come back later in the talk. But okay, you just have to remember that, okay, with this very basic type discipline, you can already represent some data types like integers. So the big important theorem about all these type systems, especially the simply type lambda calculus, is that beta reduction is strongly normalizing, which means that every reduction sequence must terminate at some point. You cannot have an infinite sequence of beta reductions. And it's also confluence that actually doesn't require typing. So what happens is that if you take any term and you write it, okay, and you reach a normal form, which you cannot reduce anymore, this normal form, because of confluence, is unique. It doesn't depend on the choices of reductions you've made. So you get canonical equivalence classes for canonical representatives for the equivalence classes of this equals beta, which you can compute and compare, and so that gives you a decision procedure for beta convertibility. Yeah. So this is all very classical. So now you can ask, you can start asking quantitative questions about this normalization and this decidability. Okay, so from the combinatorist point of view, I guess you would want to talk about what is the length of these reduction sequences. Okay, so for linear lambda terms, that is something that has been mentioned in the first talk in the morning, right? And but for computational complexity point of view, which is the point of view I'm going to take, we want to the related question would be how hard is it to decide with beta convertibility, right? So how are these questions related? Okay, so obviously, if you have a bound on the length of reduction sequences, it gives a bound on the naive algorithm to decide convertibility. But well, we will see the relation later. So first, okay, so this is the question of the length of beta reduction sequences for simply type lambda terms is actually something very well understood, a very classical topic. So I mean, at least going back to the 80s, you already have people that stated like naive bounds, which are not so far from the optimal bounds. And then there's a paper by Beckman that gives optimal bounds. So the result is as follows: you need a notion, okay, which is called the order of a type. What is the order of a type? It's a maximum number of nesting of rows to the left. So formally, if you want a recursive definition, the order of the type base type is 0, and then the order of A to B is the maximum of the order of A plus 1 and order of A. So the idea is that, okay, the 0 is a ground type, so it has 0th order data. Okay, in this base type O, and then okay, when you have a function that operates on order 0 data, it's an order 1 function, and then if you have a function that takes some order 1 argument, it's an order 2 function, etc. And you have a theorem which is that if I take a simply type lambda term, whose subterms all have types of order lower than k for some fixed natural number k, so I'm bounding the order of the subterms. Okay, maybe T has a very simple type, like T is just a Boolean, but it contains some complicated subterms, and at the end it's going to normalize to true or false, but as it is, it's not normal yet, so it has complicated subterms, maybe of order like 5 or something. Okay, so that is what you are bounding, the order of subterms. then the maximum reduction length is at most like a tower of exponential, okay, of height, which ends with the size of t, but the height of the tower of exponential is this, well, this should be k, sorry, is this bound on the order. So as an example of this phenomenon, when we take this term, which has order, whose maximum subterm order is 2, okay, so these are the so this is actually the example of the encoding of the number 2 that I showed earlier. Okay, it's and this has this type of order 2. And if you normalize this thing, okay, you get actually something with the 3 variables t and y, which has in size around 2 to the n. Why is that the case? Because okay, so this encoding of the number 2 is basically a higher order function that does something twice. If you do something twice n times, that means you do it 2 to the n times, and then what are you going to do 2 to the n times? Something which basically duplicates that argument, right? So you get 2 to the n. Okay, so here I'm talking about the size of the resulting term, but I mean, if you think about it a little bit, you can also see that you can exhibit a long reduction sequence also of this order. So you see that you match the bound for order 2, and this actually this is optimal. Okay. I mean, Beckman has a more precise results where he doesn't have a big O, he has like real the actual constants, but whatever. So that's just the idea. And okay, before going on, I just wanted to mention this thing that I also mentioned earlier, I think this morning, which is that there have been some recent results, like on studying the average case length of beta reduction sequences for simply type lambda terms of a given order. Yeah. So this was presented at CLA 4 years ago. Yeah. Okay. So now let's talk about complexity instead. Okay, so I mean, so we have this result which tells us how much time we're going to take if you want to reach the normal form. Well, like in a stupid way, you just reduce without making any clever choices of indexes, and we reach a normal form eventually. Okay, so this if you do this naive algorithms, you compute the normal forms and compare, you get something which, okay, for terms whose subterms have order lower than k, you get you can check convertibility in time, like tower of exponential of height k, ending on polynomial in n. And so this means that you're in kx time, okay, when you have a fixed k. This is a class called kx time. But you can actually do better. Okay, so here, okay, this theorem is stated for a special case where the term that you want to look at has type bool, and what you want to check is whether it converts to true. But I mean, similar improvements can be obtained by for arbitrary terms. I mean, as long as you bound the order, but not necessarily of type bool. Just maybe we have less precise results. I'm not sure exactly, but anyway, so you have a striking phenomenon here, which is, okay, you take this simple term, simply type lambda term of type bool. Now you have the bound. Instead of being k, the bound on the order of the subterms is like 2k plus 2 or 2k plus 3. And this gives you and you can actually do this in kx time or kx space, respectively, depending on whether you're even or odd. Okay, and this is optimal because the problem is like kx time complete, respectively kx space complete. So you see that the optimal way to check convertibility when you fix this bound of the order is actually like a tower exponential of half the height you would expect from this naive syntactic thing. It's because, okay, you can basically go halfway, like divide the order by 2 by these syntactic means, and then for the rest you have some semantic tricks to finish the job. in the algorithm. And it's quite a nice algorithm, but a bit complicated. But so yeah, okay. It's just to say that what you observe on the quantitatively on the syntax is like it doesn't give you exactly the optimal way of solving this problem from the point of view of computational complexity. In any case, okay, if you are interested in having something without mentioning a boundary order, you get immediately as a corollary of the hardness part. I've said this is complete for K-time, so it's hard for K-time. Okay, from this you get as a corollary that when you don't bound the order, the beta convertibility problem, well, it's decidable, but it's not in any of the K-time classes. So we say that it's non-elementary, okay, because the class of so-called elementary recursive functions is a union of all these K-time. Right. And okay, so this I'm stating it as a corollary of Theru's result, but it's the non-elementariness of beta convertibility was already known in the 80s. It's a result of static. All right. So we have this well-known old result. Okay, and we've seen that. Okay, so if I do things, even if I take my naive algorithm, actually, I'm not so far from elementary because I have a tower of exponentials of reasonably increasing height. Okay, so we should be in some complexity class which is just beyond elementary. So can we be more precise? And that is actually something I think surprisingly few people know in the lambda calculus community. Because okay, everybody knows this non-elementary thing, but there are few people who are able to say something more precise than non-elementary. But actually, well, there is a notion in the literature just for that. It's just that it's very recent. It's less than 10 years old. It was introduced by Silverschmidt, who actually observed that okay, there are all these problems and logic and verification, so including the more automata theoretic parts of logic and computer science, like Petri nets or whatever, where you have decision problems with very high complexities. So he introduced a whole bunch of very big complexity classes, which and he said, okay, these things appear everywhere. And the lowest of the complexity classes he introduced was this thing called tower, which is the class of problems solvable in the power of exponential of elementary height in the input side. So elementary being any K-time, so this looks big, but it's just because you want the class to be closed in the elementary reductions that you make it this big. Okay, so as to get a very robust notion. And so this is going to flatten a lot of distinctions, like the distinctions between K-time and K divided by 2 X-time that we had before. We're completely forgetting about it when we look at tower. Okay, but so the theorem, okay, which you can get if you read properly Statman's result with like the modern literature in mind, is that beta convertibility of arbitrary simply type lambda terms is tower complete. Yeah. So why is that? Okay, membership in tower, as I said, you just take this naive algorithm where you normalize with any strategy and then you compare the normal forms. Okay, and the tower hardness part is interesting. It's reduction from the satisfiability problem for a higher order quantified Boolean formula. So these are formulas like this. Okay, you know that the quantified Boolean formula problem is the canonical p-space complete problem where you have it's like SAT, except that you don't just have there exist a Boolean such that, but you can also put for all Booleans, blah blah blah. And here you allow for all functions from Booleans to Booleans, or even functions of higher orders, etc. And for instance, this formula here, okay, this is something which is trivially true. It's an example of instance for which you must answer true. Says okay, for all f from bool to bool, if there exists a bool such as f of x, then there exists a bool such as y, such as f of not of y. Okay, you just take y equals not of x, and right. So it's interesting to see the history of this thing because it's like the fact that this is non-elementary, okay, was first supposed to appear in a paper by Fisher and Meyer, and which never appeared. Right? It was like announced at the International Congress of Mathematicians that there would be a paper next year, but that never materialized. And then Harry Merson in the 90s, he gave a proper proof that it's non-elementary, simulating a Turing machine. Actually, implicitly, he shows the hardness if you know how to look at it. But anyway, if you want somewhere that you can cite with an explicit hardness claim, there's a paper in 2022, so last year, that studies restricted variants of this problem, which might be easier targets for reductions, for which they show to completeness. Okay, so there is actually a question on the TCS stack exchange about this, which is nice because Noam was the one who asked the question and I answered it. Okay. So that is a strategy to show the hardness part, and it is interesting thing is that it fails for the so-called safe case. Okay, so now I'm going to talk about this safe case. Okay, it's a bit obscure, maybe hard to motivate. Basically, so there are people who have been looking since the 70s and 80s at different ways to generate infinite trees. One of those ways is to so that is called the theory of higher order recursion schemes. You might have also heard of the keyword higher order model checking. Which is because these trees were generated by recursion schemes of some kind of models of functional programs, and then you can try to reduce like model checking properties of OCaml programs, for instance, to like checking to model checking problems on these kind of infinite trees. So actually, like the group of Japanese researchers that was looking at average case reduction lengths, they're mostly working on these kind of things too. So on the higher order model checking, and they were trying to understand why, despite the complexity of higher order model checking being terrible in practice, they were still managing to have practical algorithms for some fragment of ML. Well, turns out that their analysis didn't explain why, because they also showed that average case reduction length was grew like in towards of exponential of the order. So anyway, so the thing is, there is this natural notion on the lambda calculus side, which is you take simply type lambda terms, you add letrec. So this gives you the ability to create infinite things, and you look at the trees that this generates. And on the automata side, from the 80s, you had something called higher order pushdown automata, very simple. Well, basically machines that manipulate stacks of stacks. And they don't exactly match. So there are two ways of resolving the mismatch. One of them is to say, okay, I'm enriching higher order pushdown automata with a collapse operation. So this was done in the late 2000s by several people. And another way is to say, okay, I'm instead of considering all simply type lambda terms, I'm going to only consider the safe fragment of the simply type lambda calculus, okay, which will be defined in 2 slides. So this is just okay. I'm recalling all this background just for motivation to say that despite how artificial this safe lambda calculus may look, it arises naturally like in connections with automata theory, etc. And okay, I'll show you an example of what I mean by generating infinite trees on the next slide. But it's not important for the whole narrative. It's just motivation. Okay. So let me first show the automata theoretic point of view. So we're going to consider automata that have a finite state. So Q0 is in some finite set of control states, and then a stack, which is here is an empty stack for now. Okay, so when I read and have a Q0, what it does is that I say I spawn a node A, and in the left branch I move to state Q1 with the same stack, in the right branch I move to state. I stay on state Q0, but I add a symbol of the stack. Okay, so here I can do the same operation. So here I got Q1 with this new stack, and Q0 I added a symbol of the stack. Yeah. And then at some point, okay, I'm going to want to process this Q1. So what happens when I instead Q1, if I see an empty stack, then I just spawn C, and C is a node of variety 0, so it's a leaf and done. However, if I see a Q1 and I have something on the stack, then I pop the stack and I create a B, which is a unary node. C, and here you get this, etc., etc. So you see that this can go on, and you're going to get B, 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 C, etc. So you generate this infinite tree, and the same tree can be specified by lambda terms as follows. So you consider the church encoding of these trees, with these three kinds of nodes, where also you have, so they take a constructor corresponding to A, a constructor corresponding to B, a constructor corresponding to C. Okay, you see that the number of arguments of each constructor corresponds to the arity of the node, and they return O. Okay, and so this infinite tree is represented by the term, okay, lambda A, lambda B, lambda C. Let rec f equals lambda x ax of f of b of x in fc. So what does that mean? This means that, okay, initially I have an accumulator which I initialize with C, and that whenever I unfold the recursive definition, I say give me an A with the accumulator on the left, and then on the right the recursive procedure, but where I've added a B to the accumulator. So first you get C, but then you recurse here, and your accumulator is now BC, so on the left is on BC, and you add something to the accumulator, etc. You see how that works? Yeah. Okay, so that is the kind of thing that appears in the theory of higher order function scheme. Now you can't forget about this. It was just to motivate safety. The formal definition of safety, the thing that is which is contrived to.
Can you just go back to the previous slide?
Yeah.
So. What is the variable x? What is it playing in the lambda x?
Yeah, okay, so what does it play?
So I mean, does it? I don't quite see how to match the tree to that. So
no, but okay, the x doesn't appear in the tree, right?
Right.
But just okay, it's an accumulator in the recursion, and I mean, like since I'm calling FC, I'm initializing it to C. Okay, but when I recursively call myself here an FBX, then the next recursive call contains BC.
Okay.
Okay, so this is a BC, and then okay, I have this X here, BC, and then the next time I call myself recursively, it's BBC. So this is the one.
I see. Okay.
Yeah. Okay. So this is so the idea is, if you want a fragment of the lambda calculus that corresponds to the simple higher order push-down automata model, you're going to define something like this. Okay, you're going to define what is actually, okay, it's easier to define it negatively. What is an unsafe term? Okay, an unsafe term contains a subterm t primes. T prime contains some x as a free variable with of strictly lower order. Okay, so when I write order of x, I mean order of the type of x, and when I write order of t prime, I also mean order of type of t prime. Okay. And t prime is not applied to another subterm, so it's in a position which is either below a lambda or as given as an argument or something. So typically, okay, an example of unsafe term is this one, because okay, if you look here, okay, this like when okay, I'm writing the types of the variables as exponents. Okay, so lambda y dot x, when y has type O and x has type O, okay, this has type O to O, so it's order 1, but it contains x as a free variable, and x has type O, so it's order 0. So since 0 is strictly smaller than 1, I fit this thing here. Okay, and you see that the position is as an argument to f, so it also satisfies the second condition. But here it's safe, because if you look at any subterm, okay, so here you have a closed subterm. Here you have a subterm with a free variable f, but you see that f has a very high order, so there is no, right, it's an order 2 variable, so there's no problem, etc. Yes. Okay. Anyway, so Bloom and Ong say that β-convertibility is p-space hard on safe lambda terms. They do this by reduction from quantified Boolean formulas, but they don't manage to encode higher order Boolean formulas, what they showed before, without violating safety. So that's an interesting case where this strategy doesn't work anymore. And so they remark, okay, maybe since they restrict expressivity in a non-trivial way, they can expect that the beta-eta equivalence of convertibility, might have a lower complexity in the safe case. So that was their expectation, that maybe there is a good reason why they couldn't do it. And what I show is that actually no, it's still tower complete. And the thing is, the strategy is to, instead of reducing from higher QBF, is reduce from the problem of given a star-free expression, so something is grammar describing a subclass of regular languages. The problem of deciding whether the language is described by a star-free expression is the empty language. That is a very canonical tower complete problem, and they do provide a reduction. Okay, and I'll skip over maybe more technical things. Okay, but I just basically here I just wanted to mention that this is inspired by some work that I did on relating lambda calculus and automata theory with Pierre Pradec, and that we're reusing like ideas and techniques from this automata lambda calculus connection. Okay, in order to encode the star-free emptiness problem. Final. So to conclude, yes, well, the new thing that we show is that given a safe lambda term, it's tower complete to decide whether it goes to true. Actually, well, it's also in tower to decide beta convertibility for two arbitrary safe lambda terms, because it's already the case for arbitrary simply type lambda terms. So the membership part is not new, but it's the hardness part which is new. Okay. So maybe you should also remember that it works for the simply type lambda calculus, because that is not so well known. And the thing is, we needed a new proof technique, okay, in order to show that goes through automata theory. Okay, so final remark. So Pierre Pradec and I, we got a characterization of star-free languages. So the things described by the star-free expressions which appear in the reduction. Okay, using planar, affine or linear lambda terms. So a theme which has been treated several times at this workshop. Okay, so there is a connection. If you look at the dynamics of okay, what does it mean in terms of computations? Is planarity condition? It corresponds in some way to the difference between regular and star-free languages. That's result which is very beautiful, but for which we couldn't do the same kind of technique, those translating star-free expressions, because you had to go through intermediate functions that are just not expressible, etc. So instead, in this ICAL paper, we used a very powerful algebraic decomposition theorem for the kinds of monoids that recognize star-free languages. But here we could reuse this naive idea of how would we do to turn a star-free expression into a lambda term, and it turns out that it's precisely what we need to get this result here. So that's it. Thank you for your attention.
Well, thank you very much. Are there questions? No.
Yeah, so thanks for the very nice talk, Tito. So one question is, are linear terms automatically safe?
No, I don't think so. Oh, I forgot to mention one nice thing about safe lambda terms, which is that the automatic, well, there is a way to reduce safe lambda terms, which requires you maybe to reduce multiple lambdas at once sometimes, that avoids variable capture. Okay, so you never need to alpha rename variables when you reduce a safe lambda term, if you like allow yourself to substitute simultaneously like the three arguments of a three-argument function. Okay. And that is a property which is not at all true for for linear lambda terms. And there is actually a published paper with a small mistake because of alpha conversion of the three variables in linear lambda term, which is a paper by Mikoy Babichek and Naduman, where they thought they had the proof that normalizing linear lambda terms with that are finitely types is a first order transduction. Actually, it's not the case. It's only the case if you have a single variable name throughout all your lambda term. So.
Okay, but I have a follow-up question. Is just that it could be interesting to enumerate, say, lambda terms.
Oh, I haven't thought about that at all.
And then to enumerate them in the linear case or planar case.
Okay, more questions? So with that, thank you again, and thanks all the speakers of the morning sessions. And